Right, hello and welcome. This is question 4 for AQA's A2 Unit 5, the optional Astrophysics section. Okay. Question 4 is just kind of really based around one long answer question. Okay, there are two little calculations towards the end of the question. But mainly it's based on one big 6-mark question. Okay, and the question goes like this. In 1997, a supernova was observed, contributed to the controversial conclusion that the expansion of the universe is accelerating, therefore obviously referring to some kind of dark energy. It's asking us to explain why the observations of the supernova led to the conclusion that the universe is expanding at an accelerating rate, and why this conclusion is controversial. So basically what we need to do is we need to state what proof there is for the universe expanding at a increasing rate, okay, and why it goes against what we already think. So in other words, we need to say how we know it's expanding at an an accelerating rate, and what evidence, because obviously the opposite to accelerating at a constant, expanding at an accelerating rate is expanding at a constant rate, okay? So we need to say why it's expanding at an accelerating rate, how we know that, and how that goes against what we already know as it being a constant rate of expansion, okay? Obviously that's going to refer to Hubble's constant. But anyway, we'll get into the question. So the first thing that we need to do in this particular question is actually, because it's talking about a supernova, okay, we need to explain how we use the supernova, okay, to dictate whether something might be expanding or not, okay, basically how it's going to be moving away from us. So therefore the first thing you'd state is about the supernova, what it actually is. Okay, so remember, supernovas are kind of big collapsed stars, essentially. And there's two types, there's type 1a and type 2. Type 1a and type 1b, I can't remember what it is now, but anyway, you don't need to know the difference between the two, you just need to know that supernovas are used as standard candles. And because it says type 1a, just put the type 1a supernova can be used as a standard candle. In other words, the absolute magnitude is known. Okay, so if we know how bright it should be, okay, obviously the first thing we're going to be able to recognise is its apparent magnitude. Okay, so therefore, if we know its absolute magnitude, it will allow us to work out the distance away. Work out how far the star is away from Earth. Okay, because standard candles are used for the same type of star, not the same exact star, but the same type of star. Obviously, because once we know how far a certain star is away from Earth, it's going to kind of remain at that distance for a certain period of time. Okay, obviously until it starts moving away. But anyway, so we can use that knowledge of how bright it should be, okay, through the standard candle, what a supernova is, to work out how far it is away. And you could say that's because of the inverse square law, but that you could just put that and that's probably enough. Okay, so that's the first thing, that's basically saying what a supernova is. So, as I said, we need to explain how we know the universe is expanding at a constant rate, at an accelerating rate, and how it goes against what we already know of that it should be at a constant rate. Okay, so what we need to say is talk about the use of redshift. Okay, well, the use of redshift or the explanation of redshift. So your next point is you need to mention about redshift. Now, obviously, you should know what redshift is, but essentially, redshift is about the fact that as light gets further away, the source of light gets further away from us. That wave of light, because light is considered to be a wave, it's going to be kind of stretched. So therefore, the wavelength is going to increase, and the frequency is going to decrease. Okay, so in essence, this redshift is going to be helpful in determining the rate of constant expansion, because obviously using the idea of standard candles is going to give light a certain wavelength, so therefore as it's moved away, the wavelength is going to increase. Okay, so the redshift shows us that because the wavelength of the light is actually increasing more than we expected, so therefore it's moving further away than we expected. Okay, so you could mention about that, so basically saying that the wavelength of the light, obviously you could reference the redshift equation at this point if you wanted to. The wavelength of the light, okay, now I can't even spell, is greater than we expected, so therefore it's at a further distance away, which is what we experienced by the supernova. Okay, obviously we weren't alive then, but if it's likely to be, because from the context of the question, we're given the idea that the supernova in this particular question it's referencing to, that it's going to be showing some kind of increase in expansion. And for that to happen, what you'd say, obviously over time, we know that the universe is expanding, so after a certain period of time, we're going to expect it to be a certain distance away, in other words, light to be stretched by a certain amount of redshift, okay, so therefore we can say, well, it's likely to be in this region. But because it's actually outside this region that we expect it to be in, the wavelength of the light has been increased more than we expected, therefore it's been moved further away for that light to be stretched more, for the wavelength to be increased more than we expected. Okay, so essentially that's what you need to talk about. Is greater than expected. Obviously, you could use Hubble's law here and say we expect it to be a certain distance, but it's actually not. It's actually greater than that. Okay, but since I'm going to mention for God's sake, Hubble's law in a second, I don't think it's worth bringing it up now. So you could use redshift to explain the fact that, as I say, the light's been stretched by more, so the wavelength's been increased greater than we expected, so it's further away. So the object is further away. Okay, so obviously now we've explained kind of why it's moved further away than we expected. Okay, so therefore you could say it's expanding at an increasing rate. Okay, so the next point, okay, is kind of, so the first thing we've done is explained what the supernova is and how that's allowed us to say it's moved further away than it actually has done. Okay, so you might want to expand a bit more on this point than I've done, but anyway, it doesn't matter. So the next point we need to talk about is the fact that why this is controversial. Now, with any expanding universe theory or question, you are going to be at some point likely to relate it to Hubble's law. Okay, so obviously Hubble's law says that the velocity of an object is directly proportional to the distance. Okay, in other words, if the Earth is if the universe is expanding at a constant rate, okay, velocity of the object will be proportional to the distance it's covered. Okay, so therefore, obviously, you don't need to mention how it's created. This is just obvious, really. So therefore, if the velocity is proportional to distance, it will be expanding at a constant rate. Okay, because obviously we've got the Hubble's constant, so therefore it's going to be expanding at a constant rate. If you wanted to look at it like that, at a constant rate. In other words, it won't be accelerating, obviously. So, if it's expanding at a constant rate, this is proof, obviously, that we expect the redshift to be in this region. Okay, so therefore you could say we don't expect any increase in the rate of expansion, which is why this is controversial. Okay, so hopefully that is kind of enough information for you to be able to answer that 6-mark question. Okay, because essentially all this asks us to do is explain why the supernova, explain why the observation of the supernova, so you need to say what a supernova is, led to the conclusion that the universe is expanding at a constant rate, which we have done. So you said why is expanding at an increasing rate, okay, which is to do with redshift. As I say, you could mention here Hubble's law and say that we expect it to be a certain distance, but actually it's further than that, but then it kind of combines these 2 points. So I would keep them separate. So that's why it's expanding at an increasing rate, and then obviously use Hubble's constant and say, well, we actually expect it to be increasing at a constant rate, therefore we don't expect any increase in the rate of expansion. So it's the same thing really, but anyway, and that's because the velocity is directly proportional to the distance. So if the velocity increases, the distance covered increases, but if it stays the same, then distance covered over a period of time should stay the same, so no acceleration. But anyway, that's essentially it. Thanks. Don't think there's anything else of that part A to go through. Okay, so as I said, part A was the main juice of this question. Okay, you've kind of really finished the paper now. The next 2 little parts are calculation questions. Excuse me. I'm going to kind of see if I can fit it in the bottom here because it's not that bigger. So if I just kind of cover this off, so I don't want to rub it off in case you need it. Right, so it's again talking about the keeping with the theme of the redshift and the distance covered here. So we're told that the measurement of the shift in a certain 21 centimetre hydrogen line in the spectrum of the galaxy M84, again irrelevant, is receding at a velocity of 900 kilometres per second. So we're asked to calculate the redshift for this galaxy. So as you know, there's 2 equations for redshift that you're given. Okay. Now, based on what we're given in the question, okay. So actually, before I write that down, we need to write down all the information we're given in the question. So we're told that the velocity is receding at 900 kilometers per second. So therefore, the velocity is 900 kilometers per second, or 900 times 10 to the 3 meters per second. Okay, and if it's receding, then it's coming towards us, so we give it a plus in velocity. Okay, if it's moving away from us, then the velocity is actually considered to be negative. Okay, so hopefully that makes sense. Right, I'm sure I've got that right one. Anyway, that's the velocity, so that's what we're given. We're not actually given anything else. You might go, well, we're given this 21 centimetre hydrogen line, but that is kind of completely irrelevant because all that tells us is how wide this line is. It doesn't actually tell us anything about the shift of it, which that 21 centimetre line might be useful in the second part of the question, the latter part of the question. But as I say, the only key bit of information that we've got for B part 1 is the velocity. So it's asked to calculate the redshift, so we're going to have to work out Z. So what equation do we know that links something else that we might know, the velocity and the redshift? Well, that's obviously the equation Z equals V over C, where C is the speed of light and V is the velocity and Z is the redshift. Okay, so again it's putting simply banging numbers into an equation. So it's 900. Now it's key to convert that into to meters per second from kilometers per second. Okay, because I put the speed of light, and the speed of light is given to you in the equation as meters per second. Okay. So if you put on top kilometers per second, then obviously that would mess up the redshift equation. Okay. Now you either convert them both to kilometers per second, or leave them in, so you either convert the speed of light into kilometers per second, which you obviously could do, but it'd be a bit stupid really, because you like to make a mistake. Easiest to convert kilometers to meters, Well, it doesn't matter actually. Anyway, right, yeah, so essentially it's just banging numbers into that formula and putting it into your calculator. You should get a value of 0.003. Okay, and because we've got metres per second on top and metres per second on bottom, there's no units to go with redshift, because as it is simply a ratio, we know with any ratio question there is no units to consider. Okay, the next point we've got to consider the distance to this galaxy. Okay, now I know we've just talked in part A about the proof that this is an ever-expanding universe. However, this B is almost a kind of different question, because if you read the top part of the question where we were just talking about 4B, when I give the introduction to this new galaxy, that's the galaxy we're talking about. Okay, so for every intent and purposes of this question, we're going to be in part B assuming now there is a constant rate of expansion. Okay, in other words, V equals H0 times D, and you would assume that to be the case because obviously there's no equation that we currently are aware of that will allow us to predict the distance of an ever-expanding universe, because we don't know what that increasing rate of expansion is. Okay, the rate of increasing rate of expansion, if that makes sense. Probably doesn't, but anyway, in essence we're just going to be using Hubble's equation because we don't know any other equation that enables us to work out distance. Okay, maybe you could use some kind of weird combination of the redshift equation, but that's not to be considered. Okay, so anyway, what are we given? Well, we just worked out the velocity. Okay, we've just converted that, so I'm going to put that in meters per second, which is 900 times 10 to the 3 meters per second. Okay, we know Hubble's constant, obviously that's given in the formula sheet, and we want to know the distance. Okay, so obviously you're going to want to rearrange this equation to get D, so D is equal to V over the Hubble's constant. Okay, so it's obviously 900 times 10 to the 3 meters per second over Hubble's constant, which is 65. Oh, actually, for God's sake, 65 times 10 to the 3. This actually is quite a nasty bit of the question, especially for the last ever part of this paper. Okay, and the reason for that is because Hubble's constant, if you look in the formula sheet, is actually given in kilometers per second, and so is the original value for V. Okay, so if you're going to use meters per second, you also need to convert the Hubble's constant into meters per second, which you just times by 10 to the 3. But anyway, it doesn't matter, they will cancel out. So as long as they're both in meters per second or kilometers per second, it won't make a difference. And it's actually registered as 13.8 parsecs. Let's make sure that's correct. Okay, so hopefully that explains question 40. Thanks for watching, and we'll see you in the next video.